All right. Let me check the audio. Audio's good. Let me check the laptop. Audio looks good. Let me add a Discord. Discord is good. Let me check the stream. The stream sounds good. Let's go to this. Okay, let's continue watching this. But this is at what time? What is the time? I can't see the timestamp. Okay, let's remove CC. It's about 11:39. Let's refresh it.
Moving, or whether the Earth was moving through the ether or what. And this particular question was made a little more concrete in the early 1860s when Scottish physicist James Clerk Maxwell pulled together a ton of work by earlier researchers and inventors.
What's going on with the CC? I mean, why is it? Did I change language or something? Uh, Subtitles Hindi. Oh, I must have clicked it. English. English is a second language.
In what we now call Maxwell's equations. Maxwell's equations describe how electric fields and magnetic fields interact, and how we really shouldn't talk about electricity and magnetism.
It's the same field. It's the only field. It's the ether.
Independently, but rather that there is.
But this is literally the ether. I mean, they were thinking about the literal ether. So when it comes to electromagnetism, I don't have to convince anyone because it was always meant to be the ether. They invented the ether for the electromagnetic theory. So that's good. Okay, let's continue.
But a single phenomenon called electromagnetism.
Why does he have a mustache? Was he a pilot? Was he Was he Air Force?
It was a pretty big deal, but it wasn't central to the question of light. However, the connection between electromagnetism.
He has good hair. Like, that's good hair.
And light became crystal clear.
Don Lincoln. I think he's Irish.
When Maxwell uses
that's Irish hair.
And combine them, taking a dash of electricity and a dollop of magnetism, combined with a pinch of calculus and a generous splash of algebra. He combined his equations and showed that they predicted that there existed electromagnetic waves. Furthermore, he was able to calculate the speed of electromagnetic waves, and it turned out that his equations.
So this is an electric wave, and this is a magnetic wave. Wow, that's incredible. So they look the same. So why do they end up looking different? That they are at 90 degrees to each other. You can't see that here. So you have to be. It must be visible in the other equations that relate E to B.
Equation said that they moved at the speed of light. Mind you, this is a little different from saying that light actually was an electromagnetic wave, but it would have been a huge coincidence if it wasn't. And remember, this was before.
It would have been a huge coincidence.
Einstein published his work that showed that light was also a particle, so people were pretty convinced that Maxwell's work showed that light was simply an electromagnetic wave. However, I've glossed over something here. I said that Maxwell's equation said that the electromagnetic waves travel at the speed of light, but from the last lesson, we need to be cautious. The speed of light. The speed of light relative to what? The obvious answer was that Maxwell's equations predicted the speed of light with respect to the...
What is going on with the internet? What is going on here? No, the internet looks good. Why is it so unstable?
Luminiferous ether. And if that's true, then it meant that we might be able to measure the motion of the Earth through the ether. And that brings us to an effort in 1887 when American physicists Albert Michelson and Edward Morley performed what is now...
What is going on? What is going on here? What am I missing? Well, let me give you the link. Whoever wants to join us, I want to give you the link. It's my gift to you. The link to the Discord so you can join the Discord community. Hey, let me check the audio. Very nice. Very, very nice. So this is Albert Michelson and Edward Morley. So I don't know, like he's like Prussian European. You can see the nose. That's a European nose. I think it's well, they're both European, obviously. Both with a mustache. But this guy has long hair. Yeah, they used to have long hair.
At what is now Case Western Reserve University in Cleveland, Ohio. In lesson 3, we talked about how Thomas Young sent light through 2 different slits and made a series of bright and dark spots on a distant screen. Whether the spots were bright or dark depended on a shift between the waves coming from each of the 2 slits, which I remind you physicists call phase shifts. If the peak of one wave coincided with the peak of another wave, the result was a bright spot. If the peak of one wave coincided with the trough of another wave, the result was a dark spot. The important thing is the shift between 2 waves. So, Michelson and Morley decided to...
Oh, look at that. So that's the apparatus. Wow. So it didn't just go once, it went multiple times. So it's not just this distance, it's 1, 2, 3, 4, it's many, many, many times. Most impressive. Most impressive. He is. So, what is he looking at? And what is he looking at? Why? So, they're looking at the interference to see the interference. Wow. So, these are multiple mirrors here and multiple beam splitters here. Wow, most impressive. Let me see if I can. Where is the light coming? What is the source of the light? But why would they need 2 observations? They only need 1 observation. But it looks like there was 2 observations. How could you have 2 observations? What is going on? Where is the source of light? So, um, very impressive. So there's a big mirror and then 2 other mirrors, a big mirror, 2 other mirrors, a big mirror, 2 other mirrors. It looks like these are all mirrors, and this is, so these are all mirrors, but there's a splitter here, but the light must be coming from somewhere. What is, maybe this is the source? Where is the light coming from? Doesn't look like it's coming from here. The only thing that is different is this guy. But this doesn't seem to transmit light. There's no light. Where's the light coming from? Where's the source of the light? I don't see a source of light. And there's actually 1, 2, 3, maybe 4 beams here. No, it's 2, 1, and 1. 2, 1, and 1. 2, 1, and 1. 2. What is this arrangement? And there is a splitter here, but it's difficult to see where everything is going. But there's at least, but there's also crossing. What are these crossing? What is crossing here? Wow. So they were using at least 4 mirrors. They should have used many more. But this makes it, so I would say this looks like this is 1 meter. So it's a 1 meter arm, but at least times 1, 2, 3, I would say at least 4. So it's 4 meters. That's still very little. They should have used many, many more mirrors. When they got the null result, they should have thought long and hard and said, okay, we need more mirrors. We need a bigger setup. And you could stack up more and more and more mirrors, but the problem is with the signal keeps, you keep losing the signal over, all the mirrors, unless you have very high quality mirrors. So you need really high quality mirrors, and you know, and all this needs to rotate. But I would have stacked up, like as soon as I had the null result, I would have stacked up because they knew that they need to add more mirrors. I would have added more mirrors, just more mirrors, more mirrors, more mirrors. So every time you add 1 mirror, right? So let's assume this is the light source. Let's assume this is the light source. So it gets to here somewhere. It has to split. 1 goes straight and 1 goes left because this is where he's watching. So it splits. 1 goes that way. 1 goes straight. Then it comes back. 1 goes straight, and 1 goes that way. That doesn't make any sense. So this cannot be the source because if it did, it would split here. I don't know. But anyway, it doesn't matter. This is really fascinating stuff.
Do a similar thing, although the details were pretty different. First, let me describe their apparatus.
Wait, what?
The result was a bright spot. If the peak of one wave coincided with the trough of another wave, the result was a dark spot. The important thing is the shift between two waves. So, Michelson and Morley decided to do a similar thing, although the details were pretty different. First, let me describe their apparatus. They started with a beam of light that they shot at what is called a half-silvered mirror. A half-silvered mirror reflects half of the light and lets the other half pass through. You make a half-silvered mirror by putting a very thin reflective coating on a piece of glass. So that half-silvered mirror was positioned at a 45-degree angle with respect to the beam. That means that half the light passed through in a straight line, while the other half was reflected at an angle of 90 degrees compared to the original light. After passing through the half-silvered mirror, the two beams were traveling at right angles to one another. They then placed two full-strength mirrors to reflect those two beams of light back to the half-silvered mirror. The reflected beams both passed through and were reflected by the half-silvered mirror, and this recombined the two beams onto a screen where they could be seen. Here's where the phase thing comes into play. Depending on whether the two beams of light arrived in phase, with the peaks enhancing one another, or out of phase, with peaks and troughs canceling, the results would be either a bright spot or a dark spot. The pattern on the screen is just a little more complicated than I described, but that's the big idea. Before I get into the speed of light part of the experiment, I should say that this experiment was extremely sensitive to vibrations. After all, the wavelength of light is less than a millionth of a meter, less than a thousandth of a millimeter. Vibrations that would make one light path a tiny bit longer or shorter would cause the pattern to flicker between bright and dark spots. In fact, their equipment was so sensitive that someone stomping their foot at a distance away the length of a football field would ruin their measurements. So, to minimize the vibrations, they put their apparatus
It wouldn't ruin. They would just see a vibration.
underground. That helped a lot, but not enough. So they mounted their entire
What
apparatus
did
on
they
a
do?
heavy. So to minimize the vibrations, they put their apparatus underground. That helped a lot, but not enough.
Underground.
So they mounted their entire apparatus on a heavy sandstone block and floated the block and their equipment in a pool of mercury. Mercury, as you probably know, is a very dangerous substance that can be deadly. It's especially dangerous to unborn children. But Michelson and Morley were most certainly not carrying unborn children, and it was the 1880s, so OSHA didn't exist. I shudder to think what my laboratory safety board would say if I proposed their experiment today. But times were different, and their apparatus did suppress vibrations. Because the sandstone block was floating in a pool of mercury, you could also spin it, and this is a critical feature. So this brings us back to the ether. According to the thinking of the time, the ether permeated the entire universe. But we knew that the Earth rotates and orbits the sun, and it was likely that the sun moves through the cosmos. And that meant that it was very probable that the Earth moves through the ether. Alternatively, the ether could be thought of as a kind of a wind blowing across the Earth. Because the Michelson-Morley apparatus shot two beams of light at 90 degrees with respect to one another, that meant that they could rotate their apparatus so one arm was in the direction of the wind while the other was perpendicular to it. And if the speed of light is defined with respect to the ether, that meant in Michelson-Morley's lab, light would travel at different speeds through the two arms. If light traveled at different speeds, that would affect the phase of the waves passing through the two arms, and that would affect the expected pattern on the screen. Of course, the experimenters didn't know the direction the ether was passing through the Earth, but here's the beauty of the experiment. They could rotate their apparatus, which means that they could move the arms to be parallel to the movement of the ether or perpendicular. And even if they didn't know which was which, they would expect the speed of light between the two arms to change as they rotated it. That means that they should expect to see changes in the patterns of brightness and darkness on the screen. If they saw these changes, they would have discovered the ether. So what did they see? In a moment, totally worth of a drum roll, what they found was exactly zero, nothing. There was no change at all in the pattern of light and dark seen on their screen. And the only real
Show me the data. How do you know what they got? Did you see the raw data?
realistic explanation for this is that the velocity of light in both paths didn't change with orientation. And from that, it logically follows that the Michelson-Morley experiment killed the idea of the ether.
That's ridiculous. That's an ancient experiment. Why don't you conduct it today with, more mirrors?
Now, the idea of the ether didn't die immediately. People thought of possible explanations, like the idea that the Earth was dragging along the ether as it orbited the sun. So the ether in the vicinity of the Earth was stationary as far as the Earth was concerned. But the Michelson-Morley experiment was certainly the beginning of the end. A series of researchers thought about a variety of possible explanations, but slowly, one by one, they were all falsified until we are left with Einstein's conjecture, which is that the ether doesn't exist and that all observers measure light is traveling at a single...
But in 1920, Einstein said that the ether is gravity. So you never read his 1920 lecture. It's one page.
unique speed, which is about 300,000 kilometers per second. Physicists use the symbol c, that's a lowercase c, to indicate the speed of light. By the way, here's a bit of physics trivia. The symbol c was chosen to tie it to a certain Latin word, celeritas, which means speed or haste. Now, before I change topics, I wanted to tell you about a different method for showing the speed of light is the same for all observers. An undeniable and modern measurement demonstrates that all observers see the speed of light to be a single value. This measurement involves my specialty, particle accelerators. First, let's...
This is fascinating because it's not... Oh, that's just definitional. But so he has... But he doesn't have... This is very important. But he doesn't have... He has evidence, but he doesn't have proof. He has evidence, but he doesn't explain the reason why mechanistically it's always true. This is 100 years after Einstein, and he still hasn't thought about what's causing it because of wave mechanics. Amazing. And this is the guy that I respect the most in all. This is an experimentalist. I don't respect anyone as much as this guy. This is my number one guy. Yet he doesn't have proof from definition, but it follows from the definition of speed. You should know it. I mean, it didn't take me that long. It took me 2 weeks from the time I started doing this investigation. Why? Because these guys are so busy. I think they just never have time to stop and think. That's the problem with being busy. You should always avoid being busy. That's the worst thing. Your worst enemy is being busy. Is anyone listening to my wisdom? Of course not. No one wants to hear my wisdom. Yeah, so no one knows this, but the most important thing in life is to be lazy and to not be busy so that when something important comes along, you're available to investigate, to invest yourself in it. So be available. Don't be busy in anything. Be available.
Start with a low speed example. Suppose you're a pitcher for a professional baseball team. If you try hard, you can throw a baseball about 100 miles per hour. Sounds hard. My shoulder aches just thinking about it. But that's what they can do. Now, let's put the same pitcher in a fast moving train traveling at 100 miles per hour with respect to the track. That's a fast train in
But this is not wave mechanics.
the US, but quite slow compared.
Reality is not wave mechanics. Reality is wave mechanics, and you're not showing wave mechanics. I could have told you this 10, 20 years ago, 1,000 years ago, that it doesn't follow. You need to treat, when you talk about relativity, it's all about waves. And you know at the end that everything is a wave. Why are you talking about particles?
To, for example, the TGV in France.
And this is an expert. This is an experimentalist. He knows everything is a wave.
If we did this and a person standing stationary next to the tracks were to measure the speed of the baseball, they'd see that it was moving at 200 miles per hour. That's 100 miles per hour from the pitcher's arm and 100 miles per hour from the train itself. Pretty straightforward. You can do a similar experiment using a particle accelerator, and I want to remind you that this isn't a thought experiment. This is something we do every day. We're talking hard data here. We can start by taking an electron and inducing it to emit a photon. Let me remind you that a photon is a particle of light. We can measure the speed of light in a straightforward way by
But you know that these are waves.
simply setting up two stationary light detectors a fixed distance apart and measuring how long it takes for light to go that distance. Divide the distance by the time, and you get the velocity, and you find that it's 300,000 kilometers per second. Now, use a particle accelerator to shoot the electron down the accelerator at nearly the speed of light. And when I say nearly the speed of light, I'm talking extraordinarily close. In an old-style television, like your grandparents watched, the electrons traveled at something like 20% the speed of light. But even in the most modest modern particle accelerator, we can accelerate electrons to 99.9999999% the speed of light. In decimal form, that's 0.999, etc., for a total of 9 nines. So that is, to all intents and purposes, essentially traveling at the speed of light. Following our baseball example, if we see an electron traveling at the speed of light and it emits a beam of light that the electron sees traveling at the speed of light, then we should see that light is traveling at twice the speed of light. And if that's the case, we should expect to see this super fast beam of light arrive at the far detector in half the time it takes the electron.
That's not the question. The question is how fast is the electron seeing the photon leaving?
To travel that distance. Traveling the same distance at twice the speed takes half the time. Common sense. Except that's not what we see. The electron and emitted photon travel the prescribed distance in essentially the same amount of time.
Well, that's wave mechanics. But why would you say what usually the electron emits a photon at the speed of light relative to the electron? That doesn't make any sense. So this is just wave mechanics. I don't understand why. Why would you say this? I don't understand why you would argue this way.
Photon and electron both travel at the speed of light. And obviously, this makes no sense if the speed of the electron is added to the photon. No sense at all.
Why would you add it? Why would you add it if the reality is that everything is a wave?
It only makes sense if the photon is traveling at the speed of light, both to the point of view of the electron and to you, who sees the electron zooming along at very high speeds. Furthermore, this experiment.
What? So you think the electron is experiencing the photon at the speed of light? How do you know that? What am I missing? Let me start over the experiment. How is this related to the baseball guy?
In our baseball example, if we see an electron traveling at the speed of light and it emits a beam of light that the electron sees traveling at the speed of light, then we should see that light is traveling at twice the speed of light. And if that's the case, we should expect to see this super fast.
What do you mean the electron? How do you know what the electron sees? I don't understand.
Speed of light. In decimal form, that's 0. Use a particle accelerator to shoot every day. We're talking hard data here. We can start by taking an electron and inducing it to emit a photon. Let me remind you that a photon is a particle of light. We can measure the speed of light in a straightforward way by simply setting up two stationary light detectors a fixed distance apart and measuring how long it takes for light to go that distance. Divide the distance by the time, and you get the velocity, and you find that it's 300.
But how do you know the electron sees the photon moving at a certain speed? Did you ask the electron what it measured? I don't get it.
3,000 kilometers per second. Now, use a particle accelerator to shoot the electron down the accelerator at nearly the speed of light. And when I say nearly the speed of light, I'm talking extraordinarily close. In an old-style television, like your grandparents watched, the electrons traveled at something like 20% the speed of light. But even in the most modest modern particle accelerator, we can accelerate electrons to 99.9999999% the speed of light. In decimal form, that's 0.999, etc., for a total of 9 nines. So that is, to all intents and purposes, essentially traveling at the speed of light. Following our baseball example, if we see an electron traveling at the speed of light and it emits a beam of light that the electron sees traveling at the speed of light, then we should see.
What do you mean the electron sees traveling at the speed of light? How do you know? How do you know what the electron is seeing? I don't get it. I just don't get it.
that light is traveling at twice the speed of light. And if that's the case, we should expect to see this super fast beam of light arrive at the far detector and half
The proof makes no sense. How do you know what the electron sees? I honestly don't understand.
the time it takes the electron to travel that distance, traveling the same distance at twice the speed.
But you didn't ask the electron what it sees. So how do you conclude what the electron sees? How do you measure what the electron sees?
It takes half the time. Common sense. Except that's not what we see. The electron and emitted photon travel the prescribed distance in essentially the same amount of time. The
Wait,
photon,
what did you expect?
except that's in half the time it takes the electron to travel that distance, traveling the same distance.
But what do you mean? The speed of light is a constant. But you want to prove that the speed of light is a constant for all moving observers. What are you trying to, is the electron an observer?
At twice the speed takes half the time. Common sense. Except that's not what we see. The electron and emitted photon travel the prescribed distance in essentially the same amount of time. The photon and electron both travel at the speed of light. And obviously, this makes no sense if the speed of the electron is added to the photon. No sense at all. It only makes sense if the photon is traveling at the speed of light, both to the point of view of the electron and to you, who sees the electron zooming along at very high speeds. Furthermore, this experiment gives the same result for any time of day and any time of year. This means that
I
the
don't
electrons
understand.
no sense at all. Both travel at the speed of light. And obviously, photon travel the prescribed distance in essentially the same amount of time. The photon and electron both travel at the speed of light. And obviously, this makes no sense if the speed of the electron is added to the photon. No sense at all.
I don't understand. This doesn't make any sense. If the speed of the electron is added to the photon, no sense. I have no idea what you're trying to argue. I don't understand what you're trying to argue. Why would you add? So, but you never asked the electron what it's measuring the speed of light to be. Why would you assume that you're like the photon? You're saying the electron sees the photon traveling at the speed of light. How do you know? This is your hard evidence. This is nothing. I don't understand.
It only makes sense if the photon is traveling at the speed of light, both to the point.
Why? Why? Why would you say this? This is so ridiculous.
Point of view of the electron and to you, who sees the electron zooming along at very high speeds.
I don't understand.
Furthermore, this experiment gives the same result for any time of day and any time of year. This means that if there were any effects due to traveling through what we now know to be the non-existent ether, either in the direction of the ether flow or perpendicular to it, we'd see it. That's because the orientation.
That's not true. Your equipment that measures speed, you know it runs on light because every particle in the universe moves at the speed of light because everything is a wave at the speed of light except for the Higgs mechanism gives it the illusion that it's slowing down, but it's just bouncing back and forth. That's the illusion of mass. But really it's moving at the speed of light. So everything is moving at the speed of light. So everything is waving through the ether. So all your clocks are slowing down. You know this. So even if you are moving relative to the ether, your clocks would slow down. You would always measure a constant speed of light. He doesn't understand it. They're going to be blown away when I show them my proof. Or they're going to kill themselves.
Furthermore, experiment.
And no one is watching my show. Why is no one watching my show? My show is so delicious and nutritious.
It gives the same result for any time of day and any time of year. This means that if there were any effects due to traveling through what we now know to be the non-existent.
You wouldn't know. Even according to you, even according to modern physics, you would not know. You wouldn't know. Because we're assuming that you're waving through the ether, then as you're moving faster, the ticking is always the same ticking. It's always a tick-tock. So the time that you measure speed by is that, I mean, the time is the clock is always ticking the same to you, always. So over the same distance, you're always going to measure the same time. So you're always going to measure the speed of light c regardless of it's the speed of light or the speed of sound or the speed of whatever.
Ether, either in the direction of the ether flow or perpendicular to it, we see it. That's because the orientation of the accelerator changes over the course of the days and the years. When you get right down to it, this modern measurement is inarguable proof.
No, you need LIGO to rotate. Build a LIGO that rotates, or build it with multiple mirrors. There's so many experiments you can conduct to prove that there is ether.
That light travels at one speed for all observers. So I hope that I've convinced you that the speed of light is universal to all observers, which is a very counterintuitive concept, but
it's not counterintuitive if you consider wave mechanics. This is not just intuitive. This is the definition. If you're using a clock that works on the waves that you're measuring their speed, then the distance is the same, and the tick tocking of the clock is the tick tocking of the clock. So you're gonna get the same speeds, no matter if you're moving or not, relative to the medium.
experimentally true. This truth leads to all of the crazy sounding predictions of special relativity, which I talked about in the previous lesson.
There's nothing crazy about relativity. It's just wave mechanics.
Those have also been tested and found to be true, further validating the claim that the speed of light is the same for everyone. But there are some other fascinating facts that I thought you'd be interested in. One such thing
So anyway,
has to do with the claim that the speed of light is the same for all frequencies of light, or wavelengths, if you prefer that way of thinking about it. Remember from lesson 3 that Max Planck and Albert Einstein deduced that the energy of a photon of light depended directly on the frequency of the light. Therefore, low frequency light has low energy and high frequency has high energy. Now, for particles, a low energy particle travels at a lower speed than high energy particles. This is something you know from common experience. A high energy bullet can do more damage than a low energy bullet of the same weight and caliber. So it wouldn't be foolish to imagine that perhaps low energy light might travel at lower speeds than high energy light. But we know this isn't true. We know it to incredible precision. The way we know this is by using an epic cosmic explosion called a gamma ray burst. Exactly what causes a gamma ray burst is not known. There are several different hypothesized causes, but what we do know is that they are brief emissions of energy that are the brightest things in the cosmos. They can be seen literally from across the universe. They can be as little as 2 seconds and as long as a couple of minutes, and they emit all sorts of light, from the lowest energy radio waves to the highest energy gamma rays. The gamma rays can easily be hundreds of billions or even trillions of times higher energy than the lower energy light. It's a huge difference. As it happens, we have a variety of astronomical observatories that can see all wavelengths, from gamma rays, X-rays, ultraviolet, visible, infrared, microwave, radio waves, the whole schmear. And that means
the whole schmear.
The gamma ray burst goes off, we can time the arrival of the electromagnetic energy in all wavelengths and frequencies. One gamma ray burst occurred in 2009 with the unimaginative name GRB 090510. It exploded literally a long time ago in a galaxy far, far away, about 7.4 billion years ago. The light traveled for all that time, and the different wavelengths all arrived within a few seconds of one another. Let's think about what that means. 7.4 billion years is about 200 quadrillion seconds. The initial arrival times were all within 2 seconds. That means the various different energy photons, which means frequencies, all arrived with a difference of no bigger than 1 part in 100 quadrillion. That's unfathomably small. That's like measuring my height with a precision of about 1/100th the size of a proton, or if you're an astronomy buff, the distance to Alpha Centauri with a precision of about a foot. The different wavelength light traveled at the same speed to ridiculous precision. This measurement, combined with the observation that the speed of light is the same to all observers, says something very deep and fundamental about the universe. Mind you, we don't know exactly what it is, but it's clearly telling us something.
It's not about the universe. It's about the definition of tick-tocking. It's the definition of a clock. It's telling you something about the definition of a clock. It's telling you that all your measurements, that everything you have is a clock. Everything is a wave. But you know this from quantum field theory. Okay, 1 second. We have a message. 1 second. Oh, yes. What? Senus. Period. Vidworks. The ether field exists and we have proof. Okay, I need to watch this. How do you open? Okay. I need to move this. Wait, how do you tell him? How do you respond? This. Okay, we'll watch it. Wait, that's not what we're watching. What? Gotta look into this experiment. Alright. Alright, where are we? This guy? No, that's... We're done with this. This guy? Oh, okay, this guy.
Then return to the speed of light in lesson 16 when I talk about gravitational waves. It turns out that gravity also has a speed, and we measure that too. That's its own level of scientific awesomeness. Before that, though, we have some other fascinating topics to talk about. See you soon.
Can we travel faster than light? This video was just a sample. Watch the full series now at Wonderium. Mhm. Fascinating. So they completely misunderstand everything. It's so simple, yet they are able to misunderstand it. This is like magic. How can these geniuses not understand something so straightforward? Wait, I lost the signal. This one. Oh my god. 1 second. This should be here. Okay, so you know what? We can watch it now. Oh, I don't want to watch it. Let's watch it here.
Max Planck's matrix. This matrix is the conduit. Now, the idea that everything is connected is a very old idea. Even in science, in the late 1800s, there was a belief that there was an invisible web of energy that connects everything in the 1800s. And scientists were in a very heated debate, very controversial, as to whether or not this field exists. There was a very famous experiment that was conducted to determine if the field, called the ether field, actually existed. In the year 1887, the very famous Michelson-Morley experiment was designed to tell once and for all, is the field here or no? Yes or no, the field exists? It does not exist. In my opinion, it was a good experiment. However, it was poorly interpreted. For over 100 years, our science has been based in a belief that is incorrect. It's incorrect. Now, this is very interesting. 100 years later, 1986, the United States Air Force repeated that experiment. 1986, the United States Air Force replicated the Michelson-Morley experiment. They published the results in the very prestigious journal, Nature, the scientific journal Nature. What they found was this. They repeated the experiment with good equipment, much better equipment. The bottom line is that the field exists. They found that the field is actually there. This is reported in August 1986, the journal Nature, volume 322. They said, the field is there. And not only is the field there, it measured precisely the way that Michelson and Morley had predicted 100 years earlier. They just didn't have the equipment to work this out. Now, why don't we know about this? This should have made the cover of every major magazine and newspaper. This should have been on CNN headline news or Sky News.
That's impossible. Their prediction was wrong. They predicted that it should be different night and day and different months, but not immediately, not during just a rotation. And in their prediction was wrong. So what do you mean that the prediction was right?
But this changes everything for the scientists because the textbooks all say the field is not there. Entire careers are based on the field not being there. And now the field is there.
That's not true. It's not that anything is based on the field not being there. Einstein said it's there, so there's no contradiction. It's a simpler mechanism. It's a scientific interpretation rather than a magical interpretation. But there's no disagreement about the science. The science is the same, meaning Einstein assumed a constant speed of light. Well, you don't need to assume it if you assume the ether. But if you don't assume the ether and you just assume the constant speed of light, you basically assume the ether without saying there is ether. Plus, GR basically says ether. Quantum field theory says ether. Basically, electrodynamics says ether. So everything says ether except for you can't say ether. But everything says ether. Okay. But what was where is the source? Let me see the source.
Actually there. This is reported in August 1986, the journal Nature, volume 322.
Okay, E.W. Silvertooth, Special Relativity, Nature, volume, he says 322. This looks like 322. August 1986, page 390. 590? 322, 590?
Found that the field is actually there. This is reported in August 1986, the journal Nature, volume 322. They said, the field is there. And not only is 1986, the journal Nature, volume 300, is this. They repeated the experiment with good equipment, much better equipment. The bottom line is that the field exists.
Okay, let's look it up. Let me write it down in a side note. Max Planck. Maximus Planckicus. Okay, let me check. Let me check. Check it. All right. Let me look. Let me look. Okay. So the words are results. Results. The field exists. Exists. Just as it had been predicted! Exclamation. This looks like E.W. Silver Tooth Special Relativity Nature Volume. I don't know. It looks like 322. August 1986. Wait, somebody's talking to me. More comments from Senas General. This guy. Research, experimental detection of ether. Okay. 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 So we were. Okay. 1986, page 590. 590. Okay. Okay, let's look it up. Let's look it up. Let me copy this and just paste it somewhere. Share and this and just paste everything. Let's see what happens. The tale of an amazing experiment that proved Einstein wrong. No, in 1920 he said that the ether exists. Performed an experiment that seemed to overturn. Where is nature? Here's nature. Special relativity. This is it. 322. Cite this article. Blah blah. All right. I don't know if they're going to let us read it without paying for it. Silvertooth. Oh my god. It's so. There's no dark version of this page. Cite this article. Published 86. Nature. Is this it? This is sequencing the human genome. Where is the article? You know what we can do? We can copy the citation. Copy clean link. We need the citation. But they're not gonna let us read it, are they? Download citation? No, I need to share this article. Where is, article PDF, okay. This is the article? What is going on here? Sequencing, what is going on here? Preview, B0, references. This doesn't make any sense. How do you read? Oh, maybe download PDF? Save and downloads. Okay, let's try and open it. Let's try opening it. How do you open? Maybe Control O. Downloads. This guy. Sequencing. This is sequencing human. This has nothing to do with it. But they say it does. Mm, what page? Special relativity. Um, discuss the need for a Michelson information type test in space and raise interesting points in space about the effects of standing waves in rotation, translation, motion, optical apparatus. Some time ago, I carried out a relevant investigation using special standing wave sensor manufactured by General Electric. This photoelectric sensor incorporates a photomultiplier tube through which a laser beam can pass to be reflected back on itself by a mirror. This allows the device to scan translationally along the standing wave set by the interference in the beam. The experiment shows that the spacing between nodes in the standing wave set up by two oppositely directed light rays from the same laser source is a function of the orientation of the apparatus. The forced optical condition assuring light speed isotropy, as suggested by Aspden, is not supported by the experiment, and initial indications are that the beam modulation pattern is attributable to the Earth's motion through space. No, no. At cosmic speed commensurate with those found from isotropy assumption of 3K cosmic backbone radiation. In effect, it appears that in the standing wave, you need to report the data. Don't tell us your conclusions. In conditions, the waves move at different speeds in opposite directions relative to the apparatus, and their frequencies are the same. They present different wavelengths in the two directions and so affect the nodal spacing. A detailed report A detailed report on the experiment is available prior to eventual formal publication. Meanwhile, it is of interest to note that the optical configuration resembles that of the Sagnac experiment, the basis of the ring laser gyro technology mentioned by Aspden, Simopoulos, and Theo Charis. However, the sensor scans linearly along a section of the modulated beam. The sensor in a non-rotating system rather than being at rest as in the gyro and sensing effects of rotation. Clearly, this research will have interesting implications for the theory of relativity as foreseen by your recent leading article. It may also help us to resolve the large errors found in the global satellite positioning system. There's an error? Resolve the large errors found in. If present findings are sustained, it may not be necessary to extend the Michelson multiset tests into outer space in order to obtain positive as opposed to null. Results in interferometric tests of linear motion. Silvertooth. Star Route Box 166, Alga, Washington, USA. I need to see the data. He doesn't talk about the data. I don't know what he's saying. Sir Aspden, Simopoulos, and Theo Charis discussed the need for Michelson type test in space and raise interesting points about the effects of standing waves in rotating and translational motion of optical. Some time ago, I carried out a relevant investigation using a special standing wave. What is okay? So I need to see this setup. Like, they let you just write? Like, how can we believe you? Like, can you give us any data? Like what's the data? Don't. In effect, it appears that standing wave what are you talking about? The waves move at different speeds in opposite directions relative to the apparatus, and as their frequencies are the same, they present different wavelengths in the two directions, and so affect the nodal. I don't know what nodal spacing is. Like, could you show us the result? The detailed report in the experiment is available prior to where eventual publication. Meanwhile, it is of interest to know that the optical configuration resembles that of Sagnac, the basis of the ring laser, Aspen, whatever. However, the sensor scans linearly along a section. Come on, show us a diagram rather than clearly this research will have. I don't know. Okay, show me the data. Can you show me the data? I don't know. I don't know. What's this? Okay, share this. Experimental detection of the ether. Ernest Wilbur Silvertooth. This is the report? Okay. What is this? The Sagnac interferometer. X minus. I don't know what's going on here. This. Maybe it goes there and there. Oh, this is the Sagnac. So this is the beam splitter. It both goes there and there. Then it goes back, and that one goes here. Then this one comes back to here, and this one comes back to here. Okay, so this is the display. Yeah, it's a good. It's not so good because the angle, it should be 90 degrees between these two, not like not so not so acute. Should be more obtuse. Measurement of the one-way wavelength of light. So it goes here. I don't know. Whatever. Let's just assuming everything is well and good. References. Where's the data? Where is the data? What are you showing me? Where is the data? Where is the raw data? What's going on here? Why are you showing me equations? Why can't you show me the data? Abstract. Most of the Morley type experiments are shown to be non sequiturs because their logic fails to take into account the relationship between wavelength, and propagation velocity. Experimental demonstration of anisotropy in wavelength is described. The experimental evidence cited to support the principle of relativity derives mainly from the Maxwell experiment. Subsequent variants based on the same logic. That logic fails to take into account the relationship C equals mu lambda. If a source and receiver are co-moving, and if C, the speed of light, changes, then lambda, the wavelength, what's going on with the misspelling of wavelengths, must also change. The frequency mu cannot, or nu, cannot change, as this would result in a continuous increase of, I don't know what's going on. Romer, I remember the name Romer. Taking either leg of microsecond interferometer, the round trip transit time may be written as, I don't know what you want to say here. Which for the case C1 equals C2 equals C sums to which because in the experiment. Okay, ain't no one got time for this. Ain't no one got time for this. This is, I don't see the point. The ether field exists. Okay, we're done with this. Okay, let's close some stuff so we don't need that. And we're done with this. And I think we're just done. We have nothing else to review. That's it. That's it. What else? Okay, the human genome. Let me show you. Meanwhile, okay, you'll watch. Who's this? Who is this? What's going on? Attention. Welcome. I need to mute servers. This server should be. It is muted. Notification. I don't know. Okay. Anyway, so let's see what we got. All right. So there is nature. We're done with nature. Special relativity. We're done with that. Lorentz ether theory. Oh my God, my hand is falling asleep. Okay, Lorentz. We could still read this. Leiden is in the Netherlands. Einstein's view. We were in the middle of reading luminiferous ether, so we can read more about this. This is we did the Miller experiment. What is this? I think we've read this. Is this the Miller experiment? I don't know. I don't care. What is the movement? Yeah, we read Cora, a lot of responses. We looked into this. What is this? This is Einstein's paper. Okay, and that's it. There's nothing else. So I'm going to close everything. I'm not going to read anymore. I'm done. I'm done with everything. Yeah, I'm done with Einstein too. I don't care about Einstein unless I want to reference Einstein. We might want to reference him both in the lead-in paper or lecture and this. But first I need to just write my proof. So unified field theory, I don't care so much about that. And the proof, yeah, we're going to start writing. Let me close more stuff. I'm going to close this paper, Einstein's paper. I don't need it for now. My emails, my website, X. What's going on with X? Wow. Can someone translate her tattoos? Okay. We can read a little bit of X news. What do we got? Wow. The power, the beauty, and the colors of a breaking wave. Wow. Incredible. So much water. Oh. New Bill Maher says he will never hate Elon Musk despite relentless pressure from the left. Who is this guy? Wow, this is concerning. That
confirms that you were retaliated against because you spoke out against officials at Homeland Security who you believed were violating the law.
Yes, 100%.
The agency's goal is to bankrupt you, make you quit, die, kill yourselves, or basically preferably all of the above.
leaked government memo confirms whistleblowers were
This law
targeted.
is on the books.
Yes.
Is Homeland Security enforcing the DNA collection law?
Not fully.
As a result, are Americans less safe?
Yes.
No question in your mind.
None.
Our team sat down with 3 government whistleblowers with 7 decades of law enforcement experience. They work at Customs and Border Protection, or CBP, a division of Homeland Security.
This internal government memo confirms that you were retaliated against because you spoke out against officials at Homeland Security who you believe.
Wow, this creature is so cute. But this is its instincts to jump around like that to practice. Wow, awesome. How to pull two. Wow, amazing. Wow. and then do the same to wow, that's incredible. Wow. But don't pull up. That's the mistake. Always pull sideways. Pull as flat as you can. Dog's reaction to seeing its owner after 3 years. Yeah, dogs are amazing. Wow. Wow. Look at the excitement. Wow. Unbelievable. I'm gonna cry. I'm gonna cry. This is unbelievable. This is just um, programmed into them. Obviously, they didn't learn this behavior. This is just pre-programmed. Wow. Whoa. What? How people expected Olympic skateboarding to look like? Whoa. My God. Yeah. Sure. What it actually looks like. Okay. Come in and try the worst coffee one woman on TripAdvisor had in her life. The funniest ad copy I've collected this week. Whoa, no way. No, these people are unbelievable. How do you survive that? How do you survive that? Oh my God. Terrifying. Is there any study contradicting this one narrative? Whites are the most racist and intolerant group on earth. Reality, the exact opposite. White respondents, how Hispanic, Asian, Black. I don't know what this is about. Anyway, enough of that. Let me see. We can close. No, we cannot. This we're done with. Okay. Okay, it's 1 hour and it's already late. So I'm going to stop here. Tomorrow we're going to start working on a proof to Einstein's constant light speed postulate. hmm So we're going to go straight to the proof and then we'll write everything around. Like the abstract is later and the conclusion is later. And, any impact this might have on the universe, but this should be pretty good. When people see this, this should. I'm going to mention Einstein saying that ether, right? I'll mention the 1920 lecture that Einstein said there is ether, otherwise electromagnetic waves would not be able to travel. So that's going to soften the reaction. So maybe we'll lead with that. So we'll start with in 1920, Einstein said. So like Einstein, this is right. Don't blame me. Blame Einstein. And they're not going to be able to blame Einstein because Einstein is God. So I hope to hide behind his cloak. I'll cloak myself with Einstein. Einstein said. So we'll be safe. And then we'll just show the proof and we'll say, okay, thereby special relativity. And because special relativity sits on top of this assumption, I'm not saying special relativity is incorrect. I'm just saying there's nothing special about the theory of relativity. It's just wave mechanics. Therefore, it's just wave mechanics. And then we'll introduce our next papers. We'll write more and more papers to show that well, the rest of it, all the rest of it. And then we'll have a paper predicting exactly, giving exact predictions about an interferometer in the middle of nowhere. Should, right? if I'm moving in space, I should be able with an interferometer to show that I'm moving. So so nature, there is no conspiracy in nature. That's a separate paper. That there is no conspiracy in nature to to divulge my uniform speed, my uniform velocity. Nature reveals it. If I want this information, nature will give me this information. There's no issue. So we'll have that experiment. Anyway, there's a bunch of experiments. Hopefully, we'll gain notoriety. Okay, I think I'm gonna go kill myself now, and I'll see you tomorrow, everyone. Thank you so much for your understanding and your support. Oh, there's one person watching. That's incredible. That is absolutely incredible. All right, everyone. Mr. Oh, you're gone, and they're gone. Okay, I'm gonna end the stream, and I'll see you tomorrow. Bye.